How can a single array of size 784 represent a two-dimensional image in the MNIST dataset? If you remember the MNIST dataset, each image is 28 pixels by 28 pixels. In this lecture, we'll see an implementation of the K Nearest Neighbours algorithm in TensorFlow. The MNIST dataset has a huge number of images representing handwritten digits. These images are all normalized to be 28 by 28. Each of these images has an associated label indicating what digit that image represents. If you're interested in machine learning and pattern recognition algorithms, the MNIST dataset is a great place to start. All of the normalization and other grungy cleanup of images has already been done for you. You can focus on the pattern recognition portions. The code for this demo was originally written by Imeric Damien and is available on GitHub at this URL that you see on screen. It's a great example of a simple machine learning technique, and Imeric deserves our thanks for making it available to all of us. The objective of this algorithm is to find what digit a particular image represents. When we use K nearest neighbors, we find the distance of that image whose digit we want to identify from all other images in our training dataset. Find the image that is the closest to our test image. That image is our nearest neighbor. Find the label that is associated with this nearest neighbor, and this label is what applies to our test image as well. You've got the digit that our test image represents. This algorithm will be implemented in three steps. In the very first step, we'll get the MNIST libraries. Once we have them downloaded onto our local machine where we can access it, we will calculate the L1 distance between the test image and the entire training dataset. And the third step, after we've set these up as a computation graph, is to run the algorithm. Let's get started accessing the MNIST libraries. At the very top, we import the libraries that we need to run this code. We need the NumPy library, a numerical computation package, and TensorFlow. If you want to view the computation graph on TensorBoard, import the ML library from google.datalab as well. Turns out that accessing the MNIST dataset from within TensorFlow is very easy indeed. It's a very common operation, and there are helper libraries to help you do exactly that. The package tensorflow.examples.tutorials.mnist contains input underscore data. Input data.read datasets allow you to directly read the MNIST data. Store a reference to this dataset in a variable named mnist and store this mnist dataset in a directory named mnist underscore data. Hopefully, you remember the structure of the handwritten digit images in the MNIST dataset. Let's say you want to represent the image 4. Every image is standardized to be of size 28 by 28, covering a total of 784 pixels. The handwritten digit images in the MNIST dataset are single channel images in grayscale. A single number can be used to represent the pixel value for each image. Let's hit Shift Enter on this code cell and it'll go ahead and download the MNIST data. You can see where it's being stored by the output on screen. There is one little bit that we haven't explained yet though. When we downloaded the MNIST dataset, we said one hot is equal to true. What does that mean? This one hot notation refers to how the labels that are associated with every MNIST handwritten image are represented. This digit represents 4 and the label that will be associated with it will indicate 4. This label can be represented in what is called a one hot notation. Consider a 10-digit vector of all zeros. The only position where it will have the number 1 will be the index of the digit that is associated with this image. If you want to represent the digit 5, one hot notation will have the number 1 at index 5. The one index that identifies the value of this digit will be set to 1. The remaining indices will be set to 0. This is one hot notation. We have the MNIST data here in one hot notation. We can move on to get the training and test batches. mnist.train.next batch retrieves a batch of MNIST training data. We have 5,000 images in this batch and 5,000 associated labels in the one hot notation. The return value is a tuple which is stored in training digits and training labels. Since we are just looking at this KNN algorithm as an example, we chose to use just 5,000 images in our training dataset. Typically, in a real world problem, you'll use thousands, if not millions, of images. Similarly, mnist.test.next batch gets 200 images which form our test dataset. These are stored in test digits and test labels, respectively. In the next step, we set up a placeholder using tf.placeholder. This placeholder holds all the images in our training dataset. The placeholder tensor holds data of type float and its shape is none, 784. This is the shape that is used to represent the list of images in our training dataset, all 5,000 of them in one batch. It's pretty clear here that the first dimension, which says none, represents the number of images that we read into this placeholder, but the second dimension is 784. Where does that come from? Similarly, the placeholder for the test digit, a single test digit, is a vector of length 784. Again, where does the 784 come from? And how can that be used to represent an image? Let's see how these grayscale images can be represented by a single vector of length 784. The dimensions of every image in the MNIST dataset is 28 pixels by 28 pixels. 28 multiplied by 28 gives us 784. That means there are 784 pixels whose value have to be represented within a handwritten digit. The pixels in any image can be thought of as a grid on top of this image. Every box within this grid is one pixel. In a grayscale image, every pixel can be represented by exactly one value, a floating point number between 0 and 1 that represents the intensity of that pixel. 0 is fully black, 1 is fully white. In this grid, the parts of the image that are whiter will have higher values of intensity. This two-dimensional grid, which represents a handwritten digit, can be unraveled to form a single vector of 784 pixels. Every row in the matrix is appended to the end of the previous row. You're placing the rows in this matrix from end to end. 28 multiplied by 28 gives you 784. The first row of this matrix is at the very beginning of the single dimensional array. At the center comes all the remaining pixels, and the last row is at the very end of the vector. This is a single dimensional array representation of a 2D handwritten digit image. That should explain why the placeholders are set up in this way. All our computations will be on single dimensional arrays, which makes things easier to understand. The next step is to set up the computation of L1 distance. The L1 distance is a measure that we'll use to find that image in the training data set that is the nearest neighbor to our test image. Let's look at the computations of this L1 distance using arrays in some detail. The innermost operation that we perform is tf dot negative on our test digit. Visually, let's consider that we have these two arrays, one representing the training digit on the left and one representing the test digit on the right. We don't perform any operation on the training digit, but we calculate the negative of the test digit. Tf dot negative, when applied to an array, simply flips the sign of all elements in that array. The original elements representing each digit were pixel intensity values. These are now negated. They'll be either 0 or a negative value for our test digit. Once we have the negative, the next step is to call tf.add on the training digit and the negative of the test digit. We have the array representing the training digit on the left. We add it to the negative of the array representing the test digit on the right. This is the result that we get. Some of these numbers will be positive. The other elements in the resultant array will be 0 or negative. Once we have the vector that is the result of the add operation, we apply tf.abs to find the absolute value of every element in the resultant vector. So here is the result that we have for add for different images in the training dataset against our single test image. tf.absolute will find the absolute values for each element in the vector. Absolute values basically mean that any negative number in the array will be converted to its positive equivalent. Positive numbers and zeros will remain as is. If you look on screen, all numbers in orange have had their sign flipped because of the absolute. At this point, we have a vector representation of the L1 distance between the test digit and each of the training digits. We can reduce this vector representation to a single digit by calling tf.reduceSum. Reduce sum will calculate the sum of all digits in that vector to give you one value. For example, here we have the tf.reduce underscore sum of 1, 1.5, and 1.2. Once we have the L1 distance representations down to a single digit, we can call tf.argmin on the resulting list of single digit distances. This will find the index of the nearest neighbor to the test digit, the one whose L1 distance from the test digit has been calculated to be the smallest. In our example here, tf.argmin will give index is equal to 0. The training digit at this index is the nearest neighbor to our test digit. Now that we have all the computation set up, we are ready to run our graph. The first step is to initialize all the variables that we use using tf.globalVariablesInitializer. Use a with statement to initialize the session variable and call session.run on init. Set up a for loop that iterates over all the test digits. We want to find the nearest neighbor for each test digit in turn, and we do it within this for loop. Run our prediction computation for each test digit against the entire training data set. Each result will give you an NN index. The NN index is the nearest neighbor for that particular test digit. Use this NN index to index into the training labels to find what handwritten digit was the nearest neighbor of our test digit. Run np.argmax to find the real digit. Convert it from one hot notation to a real number using np.argmax. We'll see a visual representation of how np.argmax works. Let's say this is the one hot notation that represents the digit 4. np.argmax will find that index in this vector which holds the maximum value, which in one hot notation is the index 4. The training labels will give you what label we predicted for that particular test image, and the test labels will give you what the true value of that label was. You can compare them to see how accurate this algorithm is. If the digit identified by the KNN algorithm is equal to the test label for that digit, you increase the accuracy of your algorithm. Just go ahead and run this computation graph. You'll get a bunch of test digits, figure out what the predictions are, compare them with the true label, and you'll see that our accuracy is pretty good, 92%. An image of a handwritten digit in the MNIST dataset is 28 pixels by 28 pixels. The image is in grayscale, which means that every pixel within the image can be represented by a single floating point number between 0 and 1. This number represents the intensity of that pixel. If you unravel the 28 by 28 matrix row-wise such that every row is tacked on to the end of the previous row, you get a single vector that is 784 pixels long. Pixel values in this vector is our image representation.